Hello friends, in today's video we are going to study about these 3 points: work done by a gas, positive and negative work, and first law of thermodynamics. In last video we have seen about heat, internal energy and work. In last video we have seen that when heat energy is supplied to a system, then internal energy of the system increases. At the same time, work is done against expansion. In today's video we have to derive the expression for that work done by a gas, and at the same time the work done by the system or the gas can be positive or negative. Today we have to see in which case the work done by the gas is taken as positive and in which case the work done by the gas is taken as negative. So first of all we will derive expression for work done by a gas. Consider a cylinder containing gas. That cylinder is fitted with a frictionless, movable and massless piston. This piston is such that it has a zero mass. It is frictionless, that means when it moves up or down, then there is no friction between surface of cylinder and that piston, and this is movable. It can move in upward or downward direction in this way. Let initial position of the piston is shown by these dotted circles, and final position when that piston moves in upward direction is shown here. Let A is area of cross section of that piston. Imagine that piston is circular and A is area of cross section. We know that these gas molecules are in a state of random motion, due to which these gas molecules constantly collide on wall of the cylinder as well as on this surface of piston, due to which they exert a force on the piston, and due to this force the piston moves in upward direction, and let dx is a small infinitesimal displacement. Infinitesimal means very very small displacement through which this piston moves in upward direction. So we know that whenever there is a force acting on a body due to which there is a displacement, then there is work done. That work done is given by the formula force into displacement. Here F is the force exerted by gas molecules on this piston, area of which is A. Due to this force this piston moves through a distance dx. The work done is given by W equal to F into dx. Suppose this is equation number 1. But we know that pressure exerted by gas molecules on the wall of the container as well as on this surface area A of the piston is given by pressure is equal to force per unit area. This is basic formula of pressure. From that we can write force equal to pressure into area. Keep this value of force in equation number 1. We get this equation number 2. We have just kept this value of force, which is P into A, pressure into area, in equation 1, and we have got this equation: pressure P into area of cross section of this piston and dx distance. But we know that this quantity A into dx is nothing but volume. This is increase in volume, as this distance dx is infinitesimal. Infinitesimal means very very small. Here in figure you can see this distance to be a large, but actually it is infinitesimal distance, means it is very very small. It is so small that it is nearly equal to 0, not 0, it tends to 0. So when this piston moves in upward direction, then there is change in volume, there is increase in volume. That increase in volume is given by dV equal to A into dx. This cylinder is cylindrical, and therefore when this piston moves in upward direction, this additional volume is also cylindrical, and volume of cylinder is, we know, pi r square h. pi r square means this area of circle, that is A, and h means height. In this case that height is dx. So A into dx is this volume, or increase in volume or change in volume of the gas. Keep this value of dV in equation number 2. So we get this equation number 3. This P pressure as it is, this A into dx is replaced by dV. This is work done by the system in bringing out this infinitesimal change in the volume. This is work done when there is a very small change, infinitesimal change in volume. That means this volume, change in volume is so small that it tends to 0. It is approximately equal to 0. So this is formula for work done when there is a change in volume of a gas. If suppose initial volume of this system was Vi and final volume of this system is now Vf. Initially the piston was at this position in this figure, you can see here. So initial volume of the gas was Vi suppose. Now due to expansion the piston moves to this new position and final volume now increases, and that final volume is suppose Vf. So total work done in changing the volume from Vi to Vf can be obtained by integrating equation 3. So integrate this equation 3. So we will get the total work done, integration of P dV. P is pressure, dV is volume, Vi is initial volume, Vf is final volume. After solving this, P is a constant, so integration of dV will be V. By keeping the values upper and lower limit, we get P equal to Vf minus Vi. So this is a change in volume. The change in volume in this case is small, and this is expression for work done. Remember this formula at the time of numericals. So this was the expression for work done. This is very simple part. It may be asked for 2 marks in examination. This is first part. Now the second point in today's video is positive and negative work. When will be the work positive and when will be the work negative? We have just seen that when there is expansion or there is a compression, means whenever there is a change in volume, work is done. So that work can be positive and that work can be negative, in which case the work is taken as positive and in which case that work is taken as negative. For that purpose, consider again the cylinder containing gas, which is again fitted with the same type of piston. That is, it is frictionless, it is movable, and it is massless. Here also in second case also the same cylinder with same type of piston and same gas enclosed in the cylinder. So the work will be positive when piston moves out towards right, means there is a expansion. Very simple. Whenever there is expansion, means volume increases, then work is positive, and work will be negative when piston moves in, means towards left, means volume decreases, means when there is a compression. So very simple. Whenever there is expansion, whenever volume increases, volume of gas increases, that work is taken as positive. In this case, piston moves in outward direction, while work will be negative when there is a compression, volume of gas decreases and piston moves in inward direction. So what happens when piston moves out? Then these gas molecules, we know that gas consists of large number of molecules. These molecules are in state of random motion. They constantly collide on the walls of the cylinder and also on this surface area of the piston. This molecule which is moving towards this piston, before collision it will have some speed. In case of positive work, when piston moves outward, then initial velocity is more. Velocity before collision, when this molecule collides on this piston, then its velocity before collision is more. When this molecule collides on this piston, then it exerts a force. This is not a single molecule. Here only a single molecule is shown, but actually there are very large number of molecules which are colliding on this surface of the piston, due to which all these molecules exert a force, exert a pressure on this piston, due to which this piston moves in outward direction. When these molecules exert force, exert pressure, they lose their momentum. Their momentum decreases, their momentum is transferred to this piston, and this piston moves outward. Here you can see motion of piston is in outward direction. This arrow shows that piston moves in outward direction, and the momentum, this piston gains momentum, and these molecules lose momentum. When they return, their velocity decreases. So here you can see after collision, same molecule, here arrow is shorter as compared to this arrow before collision. This arrow is longer, means its velocity is more before collision. The velocity of same molecule after collision is less. Velocity is less means momentum is less, because we know momentum is mass into velocity. Initial velocity before collision is more, means initial momentum is more. Final velocity after collision is less, means final momentum, mass into velocity is less, means momentum decreases, because the momentum, some momentum is given to the piston. Momentum decreases means molecule loses momentum. That loss of momentum will be equal to the gain of momentum of this piston. Whatever is the loss of momentum of all molecules, same will be the gain of momentum of this piston. So momentum is transferred to this piston, due to which this momentum, this piston moves in outward direction, and in this case we say the work done is positive. In second case, what happens? These molecules are in a motion once again. They are constantly collide. There are number of molecules, but in this case, this piston is moving inward. Piston actually already there is a motion of piston towards left. This piston is moving towards left. Therefore, when this molecule is moving towards this piston, its initial velocity is small. When this piston moves towards left, it exerts a force on the molecules. Now in this case, piston exerts a force on the molecules. In first case, molecules were exerting force on the piston. Here, piston exerts force on molecules, due to which when these molecules return back, their velocity increases. Here you can see the arrow after collision is longer as compared to the arrow before collision, means here velocity after collision is more, because here this piston which is moving towards left, in first case the piston was moving away, but here the piston is moving towards left. So here this piston exerts a force on these molecules, due to which velocity of molecules increases. After collision, velocity increases. Velocity increases means momentum increases. So in this case, there is increase in momentum of all molecules. Therefore, we can say molecules gain momentum, and this piston loses equal amount of momentum. In first case, molecules lose momentum and piston gains equal amount of momentum. Here, piston loses momentum and molecules gain equal amount of momentum, and therefore in this case work done is taken as negative. So here during expansion, gas molecules strike the piston. These gas molecules collide the piston and lose their momentum to it. To it means to piston. Gas molecules lose their momentum to piston. Piston gains momentum and exert a pressure on it. These gas molecules exert a pressure on the piston, During compression, when volume decreases, gas molecules strike the piston. These gas molecules are in motion. These molecules again collide on the piston, but they gain momentum. In this case, they gain momentum. They do not lose momentum. They gain momentum from piston, and piston exert pressure on the gas. So main difference here is, here gas molecules exert pressure on piston. Here piston exert pressure on gas molecules. The work done by gas on piston is positive in this case. When there is expansion, work done by gas on piston is positive, while in this case work done by gas on piston is negative. So just remember, during expansion work done by gas is positive, while during compression work done by gas is negative. But one more thing, when gas is doing work, then piston is also doing work, but here the work done by piston on gas is taken as negative. In second case, the work done by piston on gas is taken as positive. So remember, finally remember, during expansion work done by gas is positive and work done by piston is negative, while during compression work done by gas on piston is negative and work done by piston on gas is positive. This work done by piston is not important. Here just remember, this work done by gas is important. So just remember this point. During expansion, in short, remember, during expansion the work done by gas is positive, and during compression the work done by gas is negative. So remember this positive and negative work. Once again, see the difference between positive and negative work. In case of positive and negative work, in positive work, this is work done during expansion, means this is work done when volume of the system increases, while in negative work, this is work done during compression when volume of system decreases. In case of positive work, molecules lose their momentum, while in case of negative work, molecules gain momentum. In case of positive work, pressure is exerted by gas on the surrounding or on that piston, while in case of negative work, pressure is exerted on the gas by the surrounding or by that piston. Here work is done by the gas, not by the surrounding. Positive work is work done by gas on surrounding, while negative work is work done by surrounding on the gas. Main difference. This is main difference. Positive work is work done by the gas, while negative work is work done on the gas. The third point is first law of thermodynamics, which is also very simple. What is the statement of first law of thermodynamics? First law of thermodynamics states that the change in internal energy of a system is the difference between the heat supplied to the system and the work done by the system on its surrounding. This is statement of first law of thermodynamics. I will explain you the meaning of this statement, but before that I will write this first law of thermodynamics in mathematical form. This is mathematical form of first law of thermodynamics. First law of thermodynamics states that change in internal energy du, here du is a change in internal energy of a system, is the difference between difference between what? Difference between the heat supplied to the system Q minus difference between heat supplied to the system and work done by the system, this work W done by the system on its surrounding. Or the same statement can be written as, transfer this minus W to left and interchange sides, we get Q equal to du plus W, means Q means heat energy supplied to the system, is equal to change in internal energy plus work done against expansion, work done by system on surrounding. So this is very simple statement or very simple law, that is first law of thermodynamics. What is that? Whenever we supply heat to any system, then that heat energy is used for two parts. First part is change in internal energy and second part is work done by system on surrounding. For example, suppose we cook food in a pot, then we supply heat energy to that food. Then what happens? This heat energy supplied, see here, you can see heat energy supplied. This heat Q, that is heat Q here. Suppose that heat energy supplied by this gas is 1000 joule. Then this 1000 joule heat energy, some part of that 1000 joule, that heat energy is used to do external work against expansion, and remaining heat energy is used as an internal energy, converted into internal energy. Internal energy means temperature increases. So when we cook this food, then you can see here there is an expansion of this mixture of water and that food. So there is the expansion, means this system is doing work. You can see here expansion, volume increases, means work is done. So that 1000 joule heat energy is used, number one, for this expansion work. At the same time, temperature increases, internal energy increases. Temperature increases means internal energy increases, because temperature depends on internal energy. Internal energy of the system increases. So if 1000 joule of heat energy is supplied here, then some part of that will be used for cooking the food, that means internal energy, and remaining part will be used to do the work against this expansion. Here you can see this expansion. Here suppose 1000 joule heat energy is supplied by gas, and for expansion suppose 200 joule energy is required. So total 1000 joule is supplied. Out of that 1000 joule, 200 joule is used for expansion, size of that food increases. Then 1000 minus 200 joule, that is the internal energy due to which temperature of this system increases. First law of thermodynamics states that a change in internal energy of system means a change in temperature, because temperature depends on internal energy. Due to that internal energy, that food cooks. The change in internal energy of the system is difference between heat, means 1000 joule, and the work done, 200 joule. So difference between these two. So what will be that difference? So that difference Q minus W, 1000 minus 200, that is used as the internal energy. So internal energy of the system here will increase by 800 joule. So when you supply 1000 joule of heat energy to this system, then 200 joule is used for work, that is not used for cooking. So remaining 800 joule is used as an internal energy. So this is first law of thermodynamics. First law of thermodynamics represents law of conservation of energy. We know that energy can neither be created nor be destroyed. It can be converted from one form into another form. Total amount of energy remains constant. Here also, when some heat energy is supplied to the system, say 1000 joule, then that is not destroyed. This 1000 joule heat energy is converted into other form of energies like internal energy and work. Total energy remains constant. Initially, the total heat energy was 1000 joule, that is converted into work 200 joule plus internal energy 800 joule. So 200 plus 800, that is 1000 joule. So this first law of thermodynamics also represents law of conservation of energy. This first law of thermodynamics can be used to calculate internal energy of a system. We know that internal energy is energy of molecules of the system. Molecules are microscopic particles, very small particles. Their internal energy cannot be directly measured. But with the help of this first law of thermodynamics, their internal energy can be measured, because Q, heat energy, is a measurable quantity that can be directly measured. Also, the work done by the system can be calculated, can be determined. Therefore, the difference between heat and work, that is internal energy, can be determined. So, this first law of thermodynamics helps us to determine internal energy of a system. Mathematical statement of first law of thermodynamics is delta U is equal to Q minus W. Delta U is change in internal energy of the system. Q is heat energy supplied to the system, and W is work done by the system or on the system. Now we know that the quantities W and Q can be positive, negative or zero. We have just seen that work can be positive, negative or zero. When work is done by the system, then that is positive. When work is done on the system, then that is negative. During expansion, work is done by the system, that work is positive. During compression, work is done on the system, that work is negative. And sometimes if there is no expansion or compression, work done is zero. Similarly, heat can be positive, negative or zero. If heat energy is absorbed by the system, means when heat flows in, then that is positive. When heat is emitted by the system, emitted by system to surrounding, heat given out, that is taken negative. And sometimes heat energy can be zero, no heat energy absorbed or emitted by the system. Therefore, the internal energy delta U can be positive, negative or zero depending upon the values of Q and W. Consider three cases. In first case, consider this system in which heat flows in, so that will be positive, because here the system absorbs heat energy. Suppose system absorbs heat energy equal to 200 joule, and system does some work, and that work done by system is 100 joule, as this is work done by system on surrounding, that is positive. So by using first law of thermodynamics, we know delta U equal to Q minus W. Here Q is 200 and W is 100. Keep these values, we get delta U equal to 100 joule, that is greater than 0. So in this case, delta U is greater than 0 means internal energy is positive. Now consider one more example, second example. Here some work is done on the system, not by the system. Therefore that work is negative. Say work done by surrounding on the system is minus 100 joule. And suppose system gives out some energy, that heat energy is minus 200 joule, as it is heat energy emitted by the body, so it is negative. So again, by using first law of thermodynamics, delta U equal to Q minus W. Q is minus 200, this work is minus 100. Keep these values, so minus 200 minus minus 100, this minus minus will become plus. So delta U equal to minus 200 plus 100, that is equal to minus 100 joule. So in this case, this internal energy is negative, means less than 0. So you have seen in first case the internal energy is positive, in second case internal energy is negative, and now we will see the third case in which internal energy is 0. Consider again the same system in which heat flows in, means system absorbs heat energy, that heat energy is 200 joule, and system does some work done by system. This is work done by system, so it is positive. This is not work done on the system. As it is work done by system, it is positive. Say work done by system is 200 joule, Again using first law of thermodynamics, delta U equal to Q minus W. Now substitute all values. 200 minus 200 will be 0. So in this case internal energy is 0. So internal energy can be positive in first case, it can be negative like in second case, or it can be 0 depending upon the values of this Q, heat energy, and work done by the system or on the system. And finally here you will see one question in board book. We will see the answer of that question. There is a question in board book. You can see that. Can you explain thermodynamics involved in cooking food using a pressure cooker? We know that we use pressure cooker to cook the food. Why this type of pressure cooker is used to cook the food? Why? What happens when we cook the food in an open pot and same food is cooked in pressure cooker? In pressure cooker, it takes less time and less energy to cook the food, while in open pot it will take more time and also more energy to cook the food. Why? Because cooking is fast in pressure cooker just because the trapped steam increases the atmospheric pressure inside the cooker. What happens here? The steam is trapped inside this pressure cooker. In open pot, the steam spreads in atmosphere, but in pressure cooker that steam is trapped and there is no expansion of the steam. Means the pressure increases due to that steam which is trapped inside this pressure cooker. The pressure increases, and at the pressure increases, the boiling point of water increases, and this higher temperature cooks food faster. That means if you cook the same food in open pot, then we know that in open pot the pressure is atmospheric pressure, less pressure. Therefore the water boils at 100 degrees Celsius. So temperature of water cannot be increased beyond 100 degrees Celsius in open pot. But in case of pressure cooker, as the pressure increases, boiling point increases, boiling point becomes more than 100 degrees Celsius. Suppose boiling point, now just imagine, this may not be true, but boiling point increases, that is true. When pressure increases, boiling point increases. Suppose boiling point becomes 120 degrees Celsius due to pressure. That means you can heat the water up to 120 degrees Celsius in pressure cooker. So temperature becomes more in pressure cooker. Temperature of water becomes more in pressure cooker. So more temperature means more energy to cook the food. In case of open pot, you cannot increase temperature greater than 100 degrees Celsius because at 100 degrees Celsius that water will get converted into steam. But here you can increase the temperature of water greater than 100 degrees Celsius. So the food will cook easily in less time. So cooking time will be faster. At the same time, we can use first law of thermodynamics here. What happens? We know heat energy supplied to system is equal to internal energy plus work done. When the pressure cooker is used to cook the food, then the steam is trapped. Volume of this steam in this pressure cooker will remain constant. That steam will not spread in air, means volume will not increase. There will not be expansion, means for that work will not be done. So work done is approximately equal to 0. Therefore Q is approximately equal to du. So whatever is the heat energy supplied, that will be used as the internal energy to increase the temperature, and due to that this food cooks faster and requires less heat energy, less time. If that is cooked in open pot, then some work will be done, and for that work some energy will be wasted, means more heat will be required. At the same time, due to high pressure, this food, all contents in this pressure cooker will get easily mixed with one another, and that will help in cooking. So in this way, today we have seen first law of thermodynamics, positive and negative work and expression for work done. Thank you for watching this video. Thank you.